Okay, let's go ahead and get started. I'm Marvin-Theimer. I'm a distinguished engineer at AWS, and I'm the lead engineer on this effort. And what I'm going to tell you about today is how to use Kinesis. If you went to the 100 level talk last afternoon, you learned about the business propositions and values, and you got a little bit of a taste of how to use it and so forth. This talk is going to be focused on how to use it and the technical aspects of that. So I've got here a picture of the whole thing overall. And I'm mostly going to be talking about the part on the right, which is how you actually process streams of data. But I briefly want to go through the whole thing. So if you remember, Kinesis is about ingesting data and processing it in real time. We can take data from an arbitrary number of sources in arbitrary volumes. And that gets ingested at our AWS Web Service front endpoint. That data is then going to be durably stored across 3 different availability zones before we say that we've gotten it successfully from the source. And then once that data is durably available, it's available for processing by an arbitrary number of applications that can be running in parallel to each other. Now, you might have sources from a variety of places. You could have, like, the computers in your data center sending log information. You might have your browser, your website server sending clickstream information in. You might have sensors from your turbines sending information in. You might have your mobile phone sending information in. We don't care. But our scale is intended to handle that kind of thing, like all of the phones in the world, ideally. On the output side, you can do whatever you like. You could take this data, for example, and aggregate it and archive it into S3. You might do some metric extraction and then put that into DynamoDB so that you could have a real-time dashboard showing things. You might do some kind of sliding window analysis and then update the statistics from that into Redshift so that you can do more complicated queries. Or you could do a variety of other things, including sending it to your favorite other place, including, say, a storm application. So what I'm going to spend the rest of the time talking about is 3 things. I'm going to take you through a tour of the Kinesis concepts in the context of trying to implement a simplified version of the demo that you saw in Werner's keynote speech. That's a Twitter Trends service. I'm going to talk about how you might implement it using our client libraries. And then I'm going to try and situate Kinesis in the broader context of a big data ecosystem. So let's start with the first thing, a tour of Kinesis concepts. So let's suppose you wanted to implement a Twitter Trends site. Now what that is, what I'm talking about here is, let's suppose we took the Twitter Firehose, and we took that into our website, and it's going to look at what the top 10 hashtag topics are. And then basically users can go there with HTTP and ask, what's the top 10 sites using, it's a standard website, right? Now, if you ignored scale, this would be pretty straightforward in AWS. Just say make it an Elastic Beanstalk application. The problem is that the data from the Firehose is too big to handle with one box, right? So the challenge we've got is we've got to somehow divide up the work among multiple machines in order to be able to process this stuff in parallel, okay? And so now that data needs to be processed in parallel and then combined and provided to our web server so that it can go out to the client. Now the solution we're going to take from this is we're going to take a page from the MapReduce community, from the community that's already figured out how to do processing of huge batches of data. They use this concept of MapReduce. We're going to come up with sort of the streaming equivalent of that. So how would we do that? Well, we're going to divide up our work and say what we want to do is we'll calculate a top 10 locally for all the data coming into each of these machines. They'll send in their top 10 estimates, and that'll get combined into a global top 10 by the web server that I've shown over here, our Elastic Beanstalk application. Now, the problem with this is the Twitter data is going to come in sort of randomly to all of these machines. I've shown here as a color the hashtag that's associated with a tweet. Now, I'm going to assume for purposes of this example that tweets come in only with a single hashtag topic in it. Now, as those of you who know Twitter know that tweets actually have multiple hashtags in it. And I'm going to leave it as an exercise to the listener at the end of this talk to figure out how you would transform a stream that has records with multiple hashtags into a separate stream, a new stream that has duplicated records with single hashtags. That should hopefully be pretty obvious how to do that when I'm done. So what we need now, if we're going to take this streaming MapReduce idea, is we need to somehow partition all of the data that has the same topic and group it together so it arrives at the same machine. So we'll do that by interjecting a box in the middle that takes the data that's coming at us randomly and sorts it by that hashtag, and then sends all of the data with the same hashtag to the same machine, like I've shown here, right? And once I have that, I can combine these. Now, you might ask, why didn't I just take the random data in each one and compute a local top 10 there? The challenge with that is you're estimating the top 10. Because, say, if I look at the red ones there, they're going to come into all the different machines. And so what I'm really doing is estimating a top 10 for some fraction of the data. And depending on skews of the distribution and so forth, you're not going to get necessarily an accurate value of top 10 without sending a substantially larger amount of data over to the green guy so that they can combine it and get statistically close. It's much simpler to do what I've shown here, which is to partition it, get an accurate top 10 estimate for all of the data that's in the subset of the red and blue guys on the top guy, the green and the orange ones in the middle, and the blue and the gray ones on the bottom. So this is just a much easier way of doing it, I would argue. And again, this is the standard way that we do it in the batch community. We're just applying the same ideas now to the streaming world. So what are the core concepts that we need to do this? Well, there's a notion of a data record, an individual tweet. There's all of the tweets that are going to go into a single type of stream, right? And I might have many different streams for many different kinds of things I want to do, right? We need a notion of a partition key, which is the thing that we're going to partition on. In this case, it would be the hashtag topic for the tweets. And we need a notion of all of the ones that are going to be grouped together and sent to a single worker. And a worker is basically the thing that's processing one of these shards, right? So a shard is all of the data that has the partition keys that have been grouped together to be sent to one single worker. That would typically be a reducer, say, if you were thinking of the MapReduce paradigm again, right? So those are the core concepts. I want to add one more thing. We order the records in a shard, and we assign a sequence number to them. So there's an exact order that's defined when records are ingested into a Kinesis stream at the beginning. And what this is going to allow us to do is a very nice form of failover by doing basically checkpoint replay. So just to recap, so how does this relate to Kinesis? Well, that box in the blue there, that blue box is Kinesis. That's the service that's taking all the data records in. And these yellow guys here are basically a Kinesis application. We call it a processing stage. And you can have many of these processing stages. So let me just recap the core concepts for you again. There's a data record. In this case, it would be a tweet. There's a stream. That's all the tweets coming from the Twitter fire hose. There's a partition key. In this case, it's the Twitter topic. And we're, for the moment, assuming every tweet record belongs to exactly one of these. Again, we would have to actually transform the fire hose into something that has that, because we have to have one single partition key that we're going to separate things by, right? There's a shard, which is all the data records belonging to a set of Twitter topics that will get grouped together and sent to one worker, which processes the records of a shard in sequence number order. And that sequence number is what gets assigned to a data record when it's first ingested by the Kinesis service, okay? Now, you could just program directly against the Kinesis service. It's a web service. We offer an SDK that lets you get to this thing directly. On the put side, for example, that's exactly what you would do. But and you could do the same thing on the get side. And let's talk about what that would look like. Basically, it's almost like processing a tape. You would seek to someplace in the stream. Typically, if this were purely a real-time application, you would seek to the end of the stream, which I've designated as latest. But you could also seek to someplace else, like the beginning of the stream of all the data that's still there, or to some checkpoint place. Once you've got an iterator, you're going to just simply read forward on that iterator, right? So you'd have a loop here that basically reads records up to some maximum that you're willing to accept. You'll get that as an array of records back plus an iterator that's basically your cursor for going forward in this stream. And then you would process those records, and you're simply in this infinite loop. Now, what would that processing code look like? In this case, it's pretty simple. We just take each of the records, and we're going to update our local in-memory data structure that keeps track of our top 10. I'll show, it's basically a hash table. And then periodically, we're going to do output. In this case, we're going to write it to DynamoDB. You could send this data directly to our website, I'm going to illustrate the fact that you might want to put it into DynamoDB, because then if you had a fault-tolerant service over there, you wouldn't have to worry about connecting to it if it fails over and so forth. Or if it's down briefly, what do you do with your data? Well, we're simply going to aggregate. We're going to simply store it in DynamoDB, and that way it's one less thing that we have to worry about. But you could do it either way, right? So periodically, we write to DynamoDB, say every 10 seconds. What happens on the other side is this guy is going to sit in an infinite loop, and he's going to scan that DynamoDB table. There will be an entry for each worker in that table. Take all of those top 10 lists that are local and merge them into a global top 10 list, and there he's got it. That's all there is to it. Now, that's not quite true. That's not all there is to it, because you had to still deal with a lot of muck in order to make this work. For example, you have to manually create the workers, and you have to figure out manually who's going to work on which shard. You've got to decide how many workers you're going to run in your EC2 instance, and you've got to decide how many of these EC2 instances to run, right? So you're doing all of this muck by hand, and what we've done is we've created a Kinesis client library that tries to take care of most of that muck for you. And what that library is it's code that you would link into your application. So the way you want to think about Kinesis applications is these are things you run yourself. So these are EC2 instances running under your account. You launch them. You provision the AMI any way you want. And that library is linked in, and it then takes care of mediating the interactions with Kinesis. So that then the code you end up writing that is primarily going to be business processing logic, as well as that configuration code for setting up your processing libraries, right? So if you had some custom library that was doing, say, image transformations or so forth, and it needed a special setup and so forth, you would be able to manage it because it's your AMI that you're creating for this thing, right? So what this library does is if it's in each EC2 instance that you run, and what it's going to do on startup is it's going to query, you're going to tell it what stream you want to process, and it's going to query Kinesis and do a describe stream web service call. And that's going to tell it how many shards there are. Now, the first guy that gets to it is going to try and create a DynamoDB table. This will be a table in your account. And in that DynamoDB table, there'll be an entry for every shard that's in the stream. So these guys, if I say had started this thing up with 3 different EC2 instances, they would each go do a describe stream to Kinesis. They'd go check the shard to see if the table exists. If it doesn't, they create it. Otherwise, they just look at it. And what they then do is they look at each of those entries and say, who's got that entry? Who owns it? Because what each of those entries has is, among other things, is a lock and a lease that is acquired by one of these worker instances. So what they're all going to do is they're going to compete to try and get this lock. In Dynamo, you can do a test and set type of lock. So exactly one of these EC2 instances will get the lock for each of the shards, and they will then spin up a worker, one of those blue ovals, in order to process that shard. They'll also do a certain amount of decentralized load balancing. They'll look at how many workers they've got on themselves, and they'll look at how many workers everybody else has by scanning that table. And if they see that they have too many workers, they'll relinquish one of their shards so that somebody else can acquire it. What that means is that the system will basically load balance. Okay? Now, that load balances across the EC2 instances that you've spun up. If you want to make that elastic, what you do is you put them in an auto-scaling group. So now what happens is you've defined an auto-scaling group for your AMI. That's going to define, you can now define a CloudWatch metric that's used to control that auto-scaling group, and that might look at, say, the load on those machines. And if the load's getting too high for some reason, then what will happen is it will automatically spin up a new EC2 instance. That won't have any workers on it, but the client library is going to go off to that shard table and try and acquire some shards. Now, what's going to happen is everybody's looking at that shard table, and they're going to see, hey, there's somebody who's not got as much load as I do. So of the other 3, they're going to kind of throw a dice and decide which guy. They'll each individually throw a dice and relinquish one of their shards. And this guy will basically be able to acquire that shard. And now I've moved some of the processing over to a new machine. So what's going on here is that basically with the client library, we can automatically do this level of load balancing and expansion and so forth. So what that would mean is if I've got some load spike, we can automatically move it across multiple machines. If the load goes back down, the auto-scaling group will push, will essentially squeeze back down. Now, one problem that you're going to run into is if the load just keeps growing and growing, I'll spin up new EC2 instances in the auto-scaling group, but at some point, I've gotten to the point where there's only one shard on each worker, right? Because the way that balancing worked is I keep moving shards off, and at some point, there's only going to be one, right? Now, if I keep growing at that point, what's going to happen? Well, the auto-scaling group's going to grow again. A new machine's going to show up. Nothing happens now because nobody's going to give up their last shard because that would make them the least loaded guy, right? Now, if you set an alarm on your CloudWatch metric here for persistent high load, then what's going to happen is these guys are going to report their load in. The alarm is going to go off. Say it goes into an SNS topic. Now you get a notification that goes to the operator of your service, the owner of twittertrends.com. That person's going to look and they're going to say, I see, I've been growing to the point where I need more capacity in my stream. And he's going to go to the AWS console for Kinesis, and he's going to issue a reshard command. He's going to split some of the shards so that there are more shards available so that we can now spin up some additional workers. So what's now going to happen is a new shard will be created. This guy down there is going to notice that there's a shard that he can grab that's not got a lock on it in the shard management table. He'll grab it, and now load goes down there. So what's going on, the way to think about the resharding in Kinesis is a human being is going to decide to add more capacity into the Kinesis stream. And what our client library does is automatically track that. So the applications currently don't do any resharding themselves. What they do is they simply they track the resharding that happens in the stream. And for the moment, that's a manual operation. You can imagine eventually we might try and automate that, but we wanted to start with something manual and give people maximum control and then watch how people use that and see where to go next with it. OK, so I've talked about how things grow and shrink and how I can take care of all the muck and so forth. One of the big things we support is fault tolerance. And there's two kinds of fault tolerance you want to think about. One is a single machine goes down, and you'd like to have some kind of automated failover. The other one is an availability zone might go down. Now, if you had put all of your EC2 instances in a single availability zone, you're now dead. Now, you can get around both of these. So let's look at how we do that. For a single EC2 instance going down, we can deal with it directly with the client library. And the way that works is, let's suppose that machine goes down. What's going to happen is these two guys, eventually, when that machine goes down, the locks that it held on the two shards that I've represented there are eventually going to expire. And everybody else is watching that table, and they're going to notice there's two shards that don't have a lock, and they're going to try and get them. Each of them will grab one because they're each going to try and move a minimum off of their current balanced load. And so what's going to basically happen is that these shards are going to be acquired, and that work is going to go to these two guys. And this happens completely automatically. Now, if you want to avoid being hit by an availability outage, an availability zone outage, what you need to do is simply have your auto-scaling group put all of your EC2 instances in multiple availability zones. And that's, again, something that you can do just specifying off the auto-scaling group. So we can handle both of these basically automatically for you. Now, you may be wondering, well, how does that failover actually work? Oh, and so let's go through that right now. So here I've shown you host A processing a shard. Let's suppose some records come into this shard, and this guy's merrily processing away. What he does is he's grabbed those two records. He's got a little counter you can see there. That's his cursor into the stream. It shows 3 right now. Let's suppose some more records come along. And so the next time he goes around his while loop, he's going to essentially call get next record, and he's going to get those guys. Now, at some point, he's going to want to do output, right? So let's suppose after these records, he updates his top 10 list to that Dynamo table. So he's going to update his shard entry for that. He's also then going to issue a checkpoint to the shard management table saying, I've seen and processed all the records through 10, and I never need to see them again. Now, that last thing there is done automatically for you. Basically, in your processing code, and we'll go through this later, you'll just say, I'm ready to do a checkpoint. It will manage writing that out to the Dynamo table for you. So in this case, he's checkpointed. So let's see what happens now when we keep going. Let's suppose some more records come in, and we're processing along. And some more records come in, and we process. And now let's suppose that we fail. So we go down. So what's going to happen is the lease is going to be lost. And so you saw down in the table that host A has disappeared. Host B is going to notice this. And they're basically going to spin up a worker after having claimed the lock for it. The client library will automatically go look at that sequence number in there and say, OK, I know that I need to start processing from here. And so I just go forward. So that's how our checkpoint replay works. Now, to give you an idea of how long this failover takes, our leases typically expire in a few seconds. So by the time the lease is expired and another host has noticed it and this has all worked, it's typically on the order of about 10, maybe 15 seconds at most, depending on whether you have some network hiccups. So you want to think of failover time as being something that's on the order of about 10 seconds, say, right? Let's see. So what that means now is that I'm going to be doing a catch-up after I've failed over, right? If it's a 15-second catch-up, I can pretty much just do that without any trouble, right? I mean, I just seek to that checkpoint, I process through it, and I've caught up very quickly. But let's suppose we're processing along, and we go down because there's a bug in our software. And so in fact, we go down, and the software on B never actually spins up a worker, or for some reason, the whole fleet goes down, and we've got to essentially go patch a bug. And so let's say for a few hours or something, we're down, or a few minutes, depending on how fast you can respond on this. Well, records keep coming in, right? The good news is Kinesis keeps those records for you. So if your sources had some buffer limit, like 10 minutes or something before they run over their disk, and have to start dropping data, we buffer this for you. We buffer 24 hours of this data before we expire it. So if you can come back up within 24 hours, no data is lost, right? Now, of course, the challenge is by the time you've come back up, this guy's going to spin up. They're going to go from their checkpoint. They're going to have a huge amount of data to go through, right? So they're going to be trying to process this as fast as they can. And the question is, well, how long is it going to take us to catch up? That's a complicated question to a certain extent. You know, the first thing that you might think about is, well, a standard shard gives you these limits on capacity for getting data in and out of Kinesis. For a given shard, you can put data in at 1 megabit per second, and you can get it out at 2 megabits per second. So if you had only one application running, then you could actually catch up, and you were running at full capacity of your shard. You were this aggressive person who decided, we're going to run at 100% capacity for some reason. Well, then you could catch up basically in the same amount of time that you were down. Now, in reality, people don't run at full utility, because then every time there's any kind of a load spike, you'd have to start rebalancing and resharding and doing everything else. So in practice, people run it much more at, say, 50% or something like that, right? And remember, shards, we've tried to make them cheap, so that's not an unreasonable thing to do, right? So now if you're running it at half capacity, even without the 2 megabytes there, you could, or if you had one application running, now you're going to catch up at 3 times speed, right? You're going to have your regular processing, and you've got 3x of that to catch up, right? So it's a variety of things that are going to determine how fast you can catch up. You also have to worry about, how fast is your application processing things. As I said, if you're running it in a way that's CPU bound on your processing side, that's going to determine how fast you can catch up. The good news is basically provisioning more shards solves this problem, right? So if we make it cheap so that it's not ridiculous to have more shards, then what you can do is provision enough shards in order to be able to handle these kinds of spikes and so forth. And the nice thing is, since we give you dynamic resharding, you don't have to decide this at the beginning and hope that it lasts until the first time that you bring things down. Basically, this just can keep running, and you can reshard as you need. But resharding only works going forward, right? I can't sort of reshard after a failure and say, now I'd like to have all the data that's already been ingested spread across more shards. That doesn't work, right? So you've got to reshard in time to be able to handle the load going forward. So let's talk about a couple of other things that you'll want to know. As I said, you can have multiple applications that run in parallel. And they basically are completely independent of each other because they each maintain their own cursor through the data. So these guys basically don't interfere, right? So the one guy can be sitting there processing along, and the other guy can be processing along. They really don't know about each other there. One of them may hiccup, may do a failover, and so forth. It really doesn't matter. The order and the timing that they have for processing through the data, that's completely independent of each other. Now, you might be wondering, why not combine these applications? Why not have one reader of the stream who then calls function calls in memory to one thing or the other? Now, obviously, I showed you earlier in this thing, Twitter trends. Suppose somebody had created Spot the Revolution that tries to detect revolutions going on in the Middle East, right, by looking at Twitter trends. If that's a separate org, they'd obviously be running it separately. But you may want to do several things for yourself within the same stream. You might have that Twitter trends thing going on, and you might want to be keeping statistics in Redshift so you can do more lengthy analysis over the last month. And you might be wondering, why not just combine these two things and just call them in memory? The challenge with this is that the checkpointing and the output rates are different from each other, and it starts getting to be a headache if you try and combine these. Let's think about this example. If we had Twitter trends, I mentioned this is going to update every 10 seconds to DynamoDB. So every 10 seconds, I'm going to do an output to a DynamoDB table, and then I'm going to checkpoint. And what that means is on failover, I'm going to go back to the last checkpoint from 10 seconds ago and process forwards 10 seconds in order to catch back up, right? Now, if I'm doing statistics, I may not want to load, I may want to aggregate things, say, at the hourly level to keep, because I'm going to keep months and months or years of data. And so here for this guy, I'm going to be outputting, say, an aggregated thing to Redshift once an hour, and I'll be checkpointing once an hour. Now, if I fail over on this guy, I'm going to go back a whole hour. Now, if I combine these two things into one worker, the question is, well, when do I checkpoint? How do I do this, right? If I say, well, let's checkpoint everybody every 10 seconds, then I'm going to be trying to upload to Redshift every 10 seconds. Redshift doesn't like that level of incremental updates. It likes big batch updates. So that's not going to work very well. But if you checkpoint every hour, then you're on failover, you're going to reprocess an hour of data to catch up. That's not very good for current trends, right? So the easiest thing to do is to simply split these apart. And that works fine. All right, let's talk about how we'd actually implement this thing. So I'm going to take you through some code. It's necessarily going to be at a high level because I didn't really have enough time to go through all the details. So this is more of a tour, right? The key message that I want to leave you with is we've open sourced, we've created a bunch of code that we've open sourced. There's the client library. There's also a bunch of library of code that we've written that's sample code that shows you how to do things like connect to S3 or upload into Redshift and so forth. And all of that code is available. So you can modify it as you like. You can go read it in detail. And so this is intended just to give you a flavor of everything. Now, in order to create a Kinesis stream, you would go through the console. There's a programmatic API if you want to do it that way, but the most common way we expect would be people would go to the console and simply create a stream. The next thing they're going to be asked is how many shards. And the primary thing that determines that is basically the data volume and the number of puts that you're going to be doing. And it's going to ask you about that. And it's going to ask you how many applications you want to run in parallel, because that'll determine how much of your read capacity you need to provision. So it'll ask you all those things, and it'll suggest a number of shards. There's also some other considerations that you'll need to take into account, and I've mentioned them. If you've got heavy processing, and that's going to be the bottleneck for your system, you'll want to take that into account. And if you have tight boundaries on catch-up, then you'll want to take that into account. Say you're doing something like a bulk archive into S3 where you might be checkpointing every hour or something like that, then you want to think about, well, what does it mean to have an hour of catch-up that I have to do, and how fast do I want to go through that? So these are considerations you'll have to take into account for yourself. The good news is you can experiment on this thing, and you can reshard later if you got it wrong. Or if things grow, if your business grows, then you can simply reshard. So it's not something where you have to get this right the first time. So now we've got our stream. How are we going to do our implementation? Well, the client library offers you this interface called iRecord Processor, and you're going to implement that interface. And there's the usual things you might expect, an initialization method and a shutdown method, and the key one is process records. Basically, the client library is going to do that loop I described, and it's going to just feed records and call this process records. It's also going to hand you a checkpointer that you can call whenever you want to checkpoint. So what process records looks like is this. For our particular example, it's going to get some records in. It's going to compute its local top 10 in memory. And periodically, it's going to decide to do output. Now, a key thing that I forgot to mention, actually, is for that checkpoint replay approach to work, I have to be idempotent in my output, right? If my output, if I don't have a completely idempotent processing approach, then if I replay things, I'm going to get a different result, right? So in this case, the way we're making it idempotent is we're going to output to that DynamoDB table every time we exceed 2,000 tweets. This is deterministic, right? Because the records are ordered, and so you're going to get exactly the same sequence of records whether you played it the first time or the second time or the third time, right? So this is deterministic, and so in this case, every 2,000 records we're going to emit to DynamoDB, and we're going to feed in the checkpointer so that it can do a checkpoint after it's updated the Dynamo table. That's basically the code you write. Again, you're going to have to create your AMI and put in an auto-scaling group and things like that together. But this is the code that you're going to write for that implementation. So we think it's fairly straightforward and simple. Just to show you again, the compute local top 10, you're going to basically have a hash table. And inside of this emit DynamoDB, you'll write to Dynamo, and then you'll call checkpoint. That's going to do that update of that table, the shard management table that I described. So that's how you would write that one application. But in fact, typically what we think is what we see customers wanting to do is a variety of things with their data. It was mentioned yesterday in the 100 talk. Big data typically goes through a life cycle where you do some amount of processing local in real time, and then you and in this particular case, that would be our Twitter Trends application. But you also want to do a variety of other things. I already alluded to the fact that it might be nice to have statistics so that I could do, say, monthly analysis of trends. So I'm going to want to take that same data and somehow aggregate it into a statistical form and upload it into Redshift. And I may want to archive this stuff, maybe in an anonymized form, and put it into S3 so that if I discover an interesting trend with my Redshift analysis, I can go actually look at the tweets and say, hey, what was going on here, right? So really, big data applications look more like this, where you've got multiple things happening to the same data stream in parallel. So what we've done is we've created a connector framework. So there's the initial client library that lets you build your basic application. This is now a second set of software that we provide, and it's offered in the form of open source sample code that allows you to do these kinds of things like upload into Redshift, archive into S3, and so forth. And I'm going to take you through a brief tour of this stuff. A key thing I want to emphasize here is the way this is factored is a particular way. You could do it a variety of other ways. Since it's open source, you can look at this stuff and you can decide for yourself how you want to tweak it. The normal case is that you'll have to write only a small amount of code in order to do things like archive into S3. But if you don't like the way the code works, or if there's something more complicated that you wanted to do, that's easy to do because this is open source, and we'll have documentation describing it. So the key concepts we provide in this connector framework are listed here. This is basically something that you would subtype in order to customize your application. There's a notion of an emitter. That's basically the way that you target a different end destination. So we have an emitter that we've already written for S3 and for Dynamo and for Redshift, but you could write your own. For example, it's very straightforward to write an emitter that would be a spout for a storm, right? So you could basically use Kinesis to get to your storm application if you had that by taking this connector code and writing something that looks like a spout for storm. We have a notion of a buffer, and that's where you would aggregate data. So if you've got if you've got records in and you're, say, doing a 1-minute statistics aggregation across all those tweets, you'd get those into the buffer. That would buffer them up, and then at some point, those would get emitted to Redshift, right? We have a notion of a transformer that allows you to take records in and do transformations on them, and we have a notion of a filter that allows you to decide that you're going to take some subset of these. If we go into these interfaces in a little more detail, they're fairly straightforward. The transformer has a method called toClass that this is going to be called to get a record from the stream and convert it into a Java data type that you would then manipulate in your connector code, right? So if I had tweets coming in as a record, which means a byte array basically, I might turn them into a Twitter record that actually shows all of the various fields and so forth. The from class is what we use to emit things. So the emitter is going to call from class in order to get a set of records of this type T and actually write them to the final destination, say S3. And the filter is very straightforward. We hand you a record, and you either say keep it or not. So if you were to look at the tweet transformer for the Twitter Trends application, this thing is going to we define a Twitter record. You would have to define that yourself. And since tweets are in JSON, basically you just need for the to class to fire up a JSON parser that is going to take that byte array and turn it into your Twitter record. Okay? On the other side, it's pretty straightforward as well. You're going to get your record in, and you're basically going to create a big string a big byte array out of this thing. And I've shown a sanitize operation in there. One way to transform things would be to say on the output, say, I'm going to anonymize the data, or so forth. I'll show you how to do aggregation in a short while. So that's basically, in order to write, say, the S3 archiver, you just saw the code. Now, the buffer interface is more complicated. And really, the main one that's interesting is the consume records call. Let's suppose we wanted to do that aggregation up to Redshift that I mentioned. Well, one way I could do it is define a consume records method that I'm going to subtype that takes in a Twitter aggregation record. So this would not be the record that I got from my stream. This would be an aggregation record. And I simply then take the aggregation records and aggregate them together until I output them. And those are going to get output. Now, what makes this work is I'm going to have a different transformer. In this case, the transformer that I'm going to use is one that on the input side takes a record out of the Kinesis stream, which is going to be a Twitter record. I'm going to parse it into a Twitter record, but then I'm going to create a Twitter aggregation record out of that that only keeps the fields that I'm trying to aggregate, right? And I'll hand that off into my framework. And then on the other side, it's going to be dealing strictly in aggregation records, so I'm going to hand that in, and I'm now going to emit that in a form that I want, say for Redshift, which in this case could be a pipe-delimited set of strings. So the emitter interface, you probably won't be writing emitters very often because we're going to try and provide you lots of useful emitters. But again, for example, if you wanted to write a storm emitter or something to go to your favorite other processing framework, real-time processing framework, you could write an emitter that allows you to basically use Kinesis as a buffering front end to go into another system like that. We're a big believer in the idea that we allow you to do what you want. And in fact, in the market of real-time processing, what we see is that the market is still experimenting with how to do things, right? There's Storm, there's the Berkeley system, streaming Spark, and so forth. There's a variety of things, and nobody really knows yet which of these are going to be the right way, or whether there is going to be one right way to do it. And so what we want to do is make it easy for you to essentially hook Kinesis into these other things, right? And so this connector framework is the first step in that direction. Okay? So let's talk about what that Redshift connector actually looks like, because it's an interesting example of using several pieces. So what I've shown here is a case where I've got the Twitter stream coming in to my processor. And what we're going to do is we're going to aggregate all of the data into S3, and then we're going to upload it into Redshift. And the reason we want to do that is because Redshift likes to do bulk upload, right? These data warehouses need to do a lot of indexing and pre-computation on data that they ingest. And so they really don't like to do this one record at a time. So what we're going to do is our processing stage is going to aggregate a bunch of these tweets. And say, for the example that we showed with Werner, we do this on a minute basis. Take all the data for a minute, write that into a bulk S3 object, and then call Redshift with a pointer to that S3 file and say, upload that file. Now, the simple version of that would imply that every one of these shards is going to create one of these S3 records that then is going to get uploaded into Redshift, right? Those are still fairly small files if you want to do this, say, every minute. Right? You could do it longer, but now you've got a longer cycle time. What you can do is actually have a two-stage system where we add another Kinesis stream and another processing stage in order to get an upload across all of your shards. The way that would work is the first processing stage still writes these S3 files, but instead of calling Redshift and saying upload that file, what it does is it puts the name of the S3 object into a second Kinesis stream. And then on the other side, we've got a processor there. And this only needs a single shard because this is going to be a low throughput stream. That guy is going to get all of the records for all of these objects. And so what he can do now is say every minute is going across all of the shards, just create a manifest file of all those S3 object names, hand that to Redshift, and Redshift will do that in one fell swoop. So here we've gotten much more batch. We've supported the batch capabilities of Redshift in a way that nicely leveraged the fact that we can compose these streams, right? And hint, hint, now, if you wanted to convert that Twitter stream from multiple hashtags to ones with duplicates in a single hashtag, how would you do it? Just one more stage, just like that, right? All right, so that's the end of the tour of these concepts. I want to end by reminding you of what the value proposition is that we're trying to provide you. Kinesis is managed, so you don't have to deal with managing all of the durable storage of this data. We handle that elasticity, and we do it in real time. We've provided you a bunch of connectors and open source libraries that will show you how to put this into the larger ecosystem. We think it's easy to write real-time applications in a fairly straightforward way with our libraries, and we've tried to make it cheap enough to where you don't have to worry about doing this. So with that, I'll be happy to take questions.